Very good morning. Welcome you all to the NPTEL course on Advanced Distribution System Analysis and Operation. Today, we will concentrate on how to solve any distribution system using OpenDSS platform. So, let us try to have a case study of IEEE 13 bus distribution system. And why 13 bus? Because it is quite peculiar. This feeder is very small and yet displays some very interesting characteristics. Short and relatively highly loaded for a 4.16 kV feeder. One substation voltage regulator consisting of 3 single phase unit connected in Y. Shunt capacitor banks do exist. Inline transformers, unbalanced spot and distribution loads. So, this is one of the perfect example for any case studies for any student or researchers to carry out distribution load flow algorithm. Let us try to solve IEEE 13 bus system load flow solutions using OpenDSS. So, we will start with actually global settings and circuit creation, and in which and then we can move to substation transformer, which uses inline RPN math, that is 0.008 ohm, to make the transformer almost ideal, so that the bus 650 site at 1.0 per unit. Two bindings, 115 kV delta on the high side and 4.16 kV Y on the load side. Then mid feeder voltage regulators, 3 single phase low impedance transformers of XHL 0.01 emulate line regulators at phases 1 to 3 of bus 650. Each bus has a control object, reg control, to maintain 122 volt with plus or minus 2 volt deadband. We can move to load definitions. Defines each node load either in kilowatt or kVAR, specifying phase connections, voltage levels and model types. Moving to capacitor definitions, to add a shunt capacitor, use command new capacitor, name the bus 1, number of phases, nominal voltage and reactive power rating kVAR. Line definitions, each new line command connect two buses using predefined line codes and lengths to build the IEEE 13 bus system feeder layout. Then we can go to switch definitions. Main switch, the 3-phase switch between buses 671 and 692 act like a normally closed breaker, letting you isolate or reclose that section with almost zero impedance. Then voltage buses align per unit basis to 115 kV, 4.16 kV and 0.48 kV levels. Then CalV computes the actual line length in per unit, and finally solve and results runs the power flow and display the voltages, currents, element power losses and regulator steps to the DSS console. I think OpenDSS is open source software available on free of cost. So, I request and recommend all the students to practice this problem through OpenDSS platform. Now, these are the simulation results. As we obtain this losses report table shows for each network element the real power kilowatt and reactive power kVAR losses in the solved power flow, plus each element share of total delivered power. At the bottom, it seems up line losses, transformer losses and the total losses. It compares that to the total load demand 3454.7 kilowatt, giving an overall loss percentage of 3.25%. Element currents for each power delivered element, example source, transformer and regulators. The report lists per phase current magnitude in ampere and phase angles showing exactly how much current each device is carrying from its connecting bus. Complex components, it also breaks each current into real plus and imaginary minus part. So, you can see both the active real and reactive imaginary currents contribution flowing through each element of the system. Now, the circuit element power flow table shows for each delivery element sources, transformers, and regulators per phase real and reactive power, how many kilowatt of real and reactive kVR are flowing into elements on each phase from the named buses. Apparent power also and the power factor can be calculated in the similar pattern. Line to ground voltages can be determined, line to line voltages also can be obtained. Now we'll get into a case study which is slightly different, management of energy storage dispatch in unbalanced distribution systems, a network using OpenDSS. So it is no more a simple system, but we like to add on energy storage to our distribution systems. Now, optimization and load flow techniques are required to determine the optimal size and dispatch of energy storage system in a distribution network. The optimal energy management scheme of storage directly impact the benefit of the system besides sizing. A significant study is done dispatch distributed energy sources in a practical low voltage distribution networks. The distribution system is integrated with PV and storage. The uncontrolled storage operation leads to losses to the operator, and frequent charging and discharging will lead to battery degradation. The present work describes a method to dispatch distributed energy system in a practical Indian distribution network using OpenDSS and MATLAB. So this is very important part where you are going to demonstrate a case study which has been carried out within the IIT Roorkee campus, and that will be demonstrated very soon. So a central storage controller is used to control the storage fleet using different dispatch models. Now, what is the background and motivation? Like changes and challenges in modern power system, as you could see, due to increased demand, penetration of uncertain and variable renewables, voltage and frequency fluctuations, and then reverse power flow, and finally non-coincident peak demand and solar peak. Now, let us focus on a IIT Roorkee distribution system where we do have bit of DRs integrated, storage integrated, and then we'll try to carry out the load flow solution using OpenDSS and MATLAB together. IIT Roorkee distribution network, which is a three-phase voltage levels of 33 kV, 11 kV and 433 volts. 4 ring systems but radial operation, multiple feeders, unbalanced loads at 433 volt, capacitor bank installed at substations, and 2.7 megawatt, there is a small error, 2.7 megawatt of rooftop PV installation. When we carried out the simulation, we have assumed to be 1.8 megawatt simulation because in 2 different phases, the PV rooftop solar has been integrated in the campus. The first phase is 1.8 and along with the second phase it become 2.7 megawatt. So there are total of 2.7 megawatt, but the simulation study do carry 1.8 megawatt rooftop solar installations. And when we talk about the energy rating, we have actually tried to have 200 kilowatt hour, 150 kilowatt hour, 100 kilowatt hour, 150 kilowatt hour and 200 kilowatt hours. So it is close to 300, 400, approximately 800 kilowatt hours of energy rating, and the power rating is close to 100, 75, 50, 75, 100. So it is for 2 hours each we are going to run it. So the technique required is time series simulation for PV output and loads due to their variability and uncertainty, detailed LV modeling as well as inclusion of multiple feeders, and 3-phase load modeling has been carried out. So as you could see, this is 1, 2, 3, 4, 5 batteries in the network, and you could see different PV systems as well as my network feeders. And first actually we modeled both load and PV modeling. A total of 1.8 megawatt of rooftop solar PV are installed over 27 distributed locations in the system. The PV system element of OpenDSS is used, which combines both PV array and the inverters. The loads are modeled as constant P and constant Q load models, divided into 3 categories, that is for hostels, residential, and departments. Load shapes are defined for all three seasons, that is summer, spring, and autumn. Storage modeling is being carried out as a peak saver, follow that is peak saver, where in this discharging mode, the storage attempts to keep the power in the monitored element within a specified bandwidth of or below kilowatt value, and it operates the same as the peak save mode, but the control is triggered by time. And in case of time mode, the storage operation is triggered by time. The storage charges or discharges according to the remaining energy capacity. And then schedule, in the discharging mode, a trapezoidal safe dispatch schedule is followed by the storage fleet. Both charging and discharging of storage follow as per unit load shape curve, and charging mode, where the storage devices will set to charge when the power of monitored element drops below a specified target. So this is what, and these are the following equations are being used. E initial and final, we expect the battery to have 50% at the beginning as well as end, and DOD, which has been broadly captured between zero point 0.8 to zero point 0.2, and lifetime of the battery has been calculated ES lifetime, and the number of cycles are being determined using this equation. Now, what are the technique to solve it actually? So, as you could see, it's basically a combination of both MATLAB and DSS. So, OpenDSS driver result analyzer. So, we have taken advantage of OpenDSS along with MATLAB. So, most of the codes and the applications of OpenDSS are being utilized efficiently. The distribution system data such as load profile, PV, and storage ratings are collected. The storage controller parameters are updated with the element least to be controlled, the reserve, and the initial state of charge. The MATLAB COM interface is initiated, and the base case and PV penetration networks. The storage is integrated with the selected parameters and operational limits. The results for various dispatch modes are analyzed for both charging and discharging. A comparative study is carried out between various dispatch models, and the one with minimum losses and voltage deviations is selected for the dispatch. Now, the workflow for interfacing MATLAB with OpenDSS. In MATLAB, launch the OpenDSS COM server and compile your main.dss file to load the circuit. From MATLAB, send a single line command, example, set storage control mode equal to 1 to switch how your battery or storage behaves. Tell OpenDSS to run 24-hour solver mode daily, number 24 solve, so you sweep through a full day operation. Read total losses and bus voltages right into MATLAB, circuit losses and all bus voltage magnitude per unit. Store them, then loop over each mode to pick the one with lowest losses and smallest voltage deviations. And these are the simulations results. You can clearly see total active and reactive power losses over 24 hours period from the spring season, losses compared to base case of storage without controlling PV integrations, and number of cycles of battery with respect to DOD value and energy stored in a battery with charging and discharge power. So, all the simulation cycles you can see, and the life of the BESS, which is the battery at 90% DOD, which is 5.2 years, and at 80% DOD, it is close to 7 years. But we are fortunate, even after 5 years, the battery is really working very successfully after integration. And now we can get into voltage of various nodes of the PV, and without PV, voltage at various nodes for different modes of operation of ESS. So these are the two case studies we can understand with PV and without PV for figure number A as well as 19.8A and 19.8B. The charge and discharge modes are identified for minimizing the system losses. So, what time it need to be charged and what time need to be discharged. So, excellent. So, what I wanted to highlight all of you, please try a little bit if you are a master students or PhD students or BTech final year students or even belongs to industry, how to carry out distribution system with distributed generations, especially storage integrated system, load flow solutions can be obtained using both OpenDSS and MATLAB in a sequential manner. Hope this lecture will help you to practice some of your problems if you have any data, or you can create a synthetic data to simulate. With this note, we stop today's lecture. Thank you very much. Bye bye.